next of the presentation is based for this analog digital converter that is used in AVR processor, and all that relevant information for that converter is in chapter 24. So all those most of the pictures in next is taken from this chapter 24. So please open the data sheet from chapter 24 to follow the next slides. If we first look for the features, it's the 10-bit resolution. And here are this conversion time. It means that how long the converter will take to make the conversion. So as the time here varies from 13 microseconds to 260 microseconds, that means that we could use different clock frequencies to make the conversion. This is of course the fast and this is the slower, but this is taking more power, and this is saving a power if we could using these lower clock frequencies. And there are 6 multiplex signal and input channels. It means that these are shared with C port. And then there are 2 pure AD converter input signals. We could look those little bit late. And input voltage range is from 0 to using voltage. And for the references, there are few options that we could use for the reference voltage. And the running mode could be single conversion or free running mode. And also we could get the information when the conversion is done. If we look at the processor block diagram, we could find the AD converter here. And here was the C port that we were checking earlier. And if you follow these lines here, it shows that this AD converter input signals goes to the same port as C port. So this means that these are shared. You could either use these pins here as digital pins by C port, or the other functionality is use for them as the AD converter input signals. And here are also 2 pure AD converter input signals. Totally you could use 8 input signals for this AD converter. And here are these analog usage voltage, reference voltage, and ground, which goes out of the chip. And here's the more detailed picture of the AD converter. Here are these input channels. These are the pins that are connected to the chip. And here's the input muxer. So it means that this multiplexer can choose one of these input voltages here and control and yield those voltages here for the comparator. The comparator is here, which will compare this input voltage to this DAC voltage. And the DAC voltage is controlled by this conversion logic. And the conversion logic is used by this data bus, which goes to CPU. And here are these reference voltage selections. So basically there are internal 1.1 volt, and then there's the reference voltages will be shown more detail in next slide. And here is the register that contains the converted data in numeric form. Here is a prescaler. We could choose the clock frequency of this conversion logic. And here are these registers that we could control we could choose that which kind of reference voltage we are using and what is the input channel that we are using. And also we could generate an interrupt request for the processor when the conversion is ready. The reference voltage was that voltage that is the maximum voltage for the input channel. And for here with this processor there are three possibilities for the reference voltage. One reference voltage could be this analog using voltage AVCC, which is usually connected to 5 volts. So it means that then that this highest input voltage, converted input voltage will be 5 volts if we connect this to 5 volts. But that is usually that we do in that way. The other reference voltage could be this internal 1.1 reference voltage that is generated internally by the chip. The third option is to use pure individual analog reference voltage that we could connect here. So if we bring our own reference voltage to our converter, we should connect it to here. And then we are of course not using these voltages. This FET will be off state, so the reference voltage will go directly from our outside circuit to our converter. And how we could choose this reference voltage is that in that registers there are, this is the register AD-MUX register. There are 2 bits in that register, RAFS1 and RAFS0. With these 2 bits we could choose that which reference voltage mode we are using. And in here in this table the meaning for those bits is explained. So for example, if we would like to use this our analog logic usage voltage for the reference voltage, we will choose it. We will choose this option. Put this S1 0 and S0 to 1. So then we are using this for the reference, this analog circuit usage voltage. The other functionality that contains in AD-MUX register is the way to choose which input channel we are using. And there are, as we talked earlier, that there are 8 possible input channels. It means that we need at least 3 bits to choose that input channel. So there are in that AD-MUX register there are 4 bits in fact, MUX 3 to MUX 0. And how we use this is that this bit combination defines which input channel is chosen. Here are these 4 MUX bits, and certain combination of these bits will define that which input channel is activated. It's quite logic, it's the binary weight form, so if we put this 1, then this lowest bit is activated and that input channel 0 is activated. Here are these MUX bits. This was that 0 bit, MUX 0 bit and MUX 3 bit, and between this with this combination we could define that which input channel is activated. And here's the MUX decoder. It controls that input MUX. Between these with these 4 bits we could choose the input channel that we are using for that certain conversion. And here's the table that shows that in which channel needs which kind of bit combination to be activated. For example, here if we put all mux bits to 0, then input channel 0 is chosen, and with lowest bit 1, input channel 1 is chosen, and so on. And here are these results, so this means that these are not used in this processor mode. And we could also input our reference voltage and 0 voltage if we would, for example, to verify that our AD converter is still working as it should be. These are the bit combination that we have to put this ADMUX register, and then we can choose the needed, wanted input channel. And how to get the real conversion started and controlled, that is done by this control and status register. And as you can see from the big picture, that's the register that controls the whole AD converter. Here are a few of the important bits in that control register. The first bit here is AD enable, so this we could say that this is the switch for the AD converter. It enables the AD converter functionality or disables that. If we put this 1, then the AD converter is active, and if we put this 0, then the AD converter is disabled and not used at all. And next bit, when we have been activated AD converter, we have to start the conversion. And there is this AD conversion SC bit, which will, by putting this 1, then the conversion will be started in the single shot mode. And then there is the trigger mode selection. By this bit we could choose the single shot mode or continuous conversion mode. And when the conversion is done, we could also get that information for this interrupt flag bit. It means that when the conversion is done, the interrupt flag bit changes its status. And activating for the interrupt functionality, there's the ADIE interrupt enable bit. With this bit we could enable the interrupts for after conversion is done. And as we earlier discussed that the conversion could be faster or slower, here are these prescale selection bits. With these bits we could choose the division factor. It means that this is the factor that the clock frequency will be divided. If we divide the clock frequency between 128, it's of course slower than if we divide that with 2. So with this bit combination we could choose how fast the conversion is. And when the conversion is done, we have to of course read the converted value somewhere. And it's the ADC register. That's the register that will contain the converted value. And as we know that this is a 10-bit converter, of course then the value of the converted value is presented with 10 bits. And as this processor is the 8-bit processor, then we can't put 10 bit to one byte or one register, because the registers are 8-bit wide. So then we have to split these 10 bits to 2 parts. So we will put 8 bits to one register and 2 bits to other register, and totally we will get then 10 bits value from the converted value. And in here there's the ADC L. It means the ADC lower register. And here are this low bit, 8 low bits of the converted value. And the other register is ADC H. It was the ADC high register, and there are the left 2 bits, the most significant bits of the converted value. And for the other bits in that register have no meaning. So we have to read 2 registers to get that 10-bit converted value. As we noticed that these input bits were shared between either this digital port C or AD converter. So we have to define somewhere, are we using these bits as digital port bits or input bits for AD converter. And this is done by this DIT-R0 register. So it means that with these bits we define the meaning of the input pins. Are they used for this digital C port or for our AD converter? And if we put the equivalent bit here, the 0, then the pin will be used by AD converter, and if it will be 0, it will be used for the C port digital pin. And with with value 1, it will be this AD converter input bit. So we could choose the functionality of each of these individual six pins by defining here either 1 or 0 to define the functionality of that individual pin. And as we remember from the original block diagram, there was 2 of these direct pins connected to AD converter, so these are all the time connected to AD converter, so we don't need to define functionality for those.